Hey there. So today we are going to be discussing the differential equations of projectile motion with air resistance. So previously on this channel we have looked at projectile motion without air resistance in 2D, projectile motion with air resistance but in 1D, and today we are going to be looking at 2D with air resistance. So as I have discussed in the previous videos, the force of air resistance is given by this formula where F sub A is the force of air resistance and V is the velocity. So, and V hat is of course the unit vector in the V direction. So using this formula, we can first of all find the acceleration. So the acceleration due to air, so the subscript A means air. So this is equal to minus C rho A over 2m V square V hat, right? Because I'm just using the fact that F equals ma. So now, since we are going to make a differential equation, we don't want all of this stuff to clutter our equation. So let's just call this entire thing as k. So A's vector is equal to minus kv square v hat. So basically the acceleration due to air resistance is proportional to the square of the velocity. So this is the acceleration due to air, but there's one more thing which is causing acceleration, and that is gravity. So the total acceleration, which is A vector, is equal to A vector plus G vector, and G vector is equal to minus 9.8 meters per second square J hat. So basically G vector is the acceleration caused by the force of gravity in its full form. So I've put the minus sign inside the vector itself. We don't need to put minus G vector over here. So just clearing that up. And now we know that A vector is the derivative of the velocity vector. So dv vector by dt is equal to A vector plus G vector. And now using this we can make a differential equation. Okay, so this is what we got so far, and now since we know the formula for A vector, we can plug that in over here. So we'll get dv vector by dt is equal to minus kv square v hat plus g vector. And now the problem here is that we have v vector over here, and we have the magnitude of v, which is just the magnitude of v vector, which is just v, and v hat. So we have the separate magnitude and direction of v vector on the RHS. So this is not really a function of v vector as such. So, and you may be thinking that we can combine the magnitude and the direction to give us the vector. That will work, but only to a certain extent, because then this will become kv times v vector, because one v will combine with v hat to give you v vector, and you'll get this. But this is also a function of the magnitude of v as well as the vector v itself. So this is a problem. So we need to bring in two variables, the magnitude of v and the direction of v. So what I thought up was that we can write v vector as v times the magnitude of the direction of v, which is v hat. So we can write use this formula on the LHS. So we'll have d of v times v hat over dt is equal to minus kv square times v hat plus g vector. And now we have two variables on the LHS, two variables on the RHS, and everything sorted out. So now what we can do is we can use the product rule, because this is a function of t. So this is actually just v of t, the speed as a function of time, and this is v hat of t. So that is just the direction in which the projectile is traveling with respect as a function of time. And similarly you can do the same over here. So everything is a function of time. So now we can use the product rule over here, because you have a product of two functions. So this implies that dv by dt times v hat, differentiating the left, plus dv hat by dt times v, differentiating the right, is equal to minus kv square. And now I'll write v hat as cos theta I hat plus sine theta j hat. And now theta, so since this is a unit vector, we can write it in this form, and theta is the direction, the angle of travel. So if our projectile goes something like this on a trajectory like this, so at any point in the xy space, the angle of travel will be theta, and the speed of travel will be v. So now we have made the direction a bit more workable with, because dv hat by dt is a bit tough to deal with as compared to cos theta I hat plus sine theta j hat. So now that we've done that, this will be much easier to work with. So we can write this as dv by dt times, now v hat is this thing, so cos theta I hat plus sine theta j hat plus, now once again you can write v hat as this, so you'll have d of cos theta I hat plus sine theta j hat over dt times v, and that is equal to this thing. So sorry, I forgot a term here. So that is equal to this thing. So we can once again use the full thing that v hat is. So it will be minus k v square cos theta I hat plus sine theta j hat. And we can also write g vector in its vector form with I hat and j hat. So this will be minus g j hat. So now g is 9.8 meters per second square, and now we have to put a minus sign because it's in the downward direction. So now we have our full differential equation over here. So v and theta are functions of time, and we have to solve for them. But now this is a problem because we have one equation with two variables, and you may think that we can't solve for the two variables then. But the thing is, this is a vector equation, so you have I hat and j hat, so you can split up the I hat and j hat and you can equate them individually, in which case you'll get two equations with two unknown functions. So we can get the two equations by separating it out now. Okay, so now let's separate out the I hat part and the j hat part. So first of all, we'll do I hat. So we'll have dv by dt times cos theta. From here we'll have, so now we can split this up into d of cos theta over dt I hat plus d of sine theta over dt j hat. So once we split it up like that, we can write this thing in terms of theta and d theta by dt. So now d cos theta by dt is, using the chain rule, it's nothing but minus sine theta d theta by dt, because theta is a function of time. So first you differentiate cos theta with respect to theta, and then you differentiate theta with respect to time, and you can do a similar thing over here and you'll get cos theta d theta by dt. So now in the x part you will have minus sine theta d theta by dt, and that is equal to the I hat part over here. So you'll have minus k v square cos theta, and now we'll do the j hat part. So for j hat we'll have dv by dt sine theta, and we'll have plus cos theta d theta over dt, and that is equal to the j hat over here, which is minus kv square sine theta minus g. So now we have two equations and two unknown functions, but that is still a problem because we have two equations and two unknown functions, and they are both differential equations. So as it is, solving one differential equation is very hard, and now we have two functions for which we have two equations and we have to solve for both of them. So this may seem a bit tough, and indeed it is, but the maths plays out in our favor a little bit. So you'll see what I mean by that. So now we can solve for dv by dt and d theta by dt individually. So we'll just solve it like an algebraic equation. So we'll consider this as x and this as y, and we have two equations in x and y, and we'll solve for them algebraically. So to solve for them individually, let's first give these equations names. So let's call this equation 1 and equation 2, because now this will make it easier to refer to. And now we can multiply equation 1 by cos theta, so 1 into cos theta, and add to that the second equation into sin theta. So what does this do? Well, if you multiply the first equation with cos theta, you'll have sin theta cos theta d theta with a negative sign, and if you multiply the second equation with sin theta, then you'll have sin theta cos theta d theta with a positive sign, so they'll cancel out, and you'll just have one equation in one variable, which is dv by dt, and then we can algebraically solve for it. So if you add these two, then first of all notice that this will become cos square, this will become sin square, and you'll have dv by dt cos square plus dv by dt sin square, which is just dv by dt. So you'll have dv by dt, and these two will cancel out as we already saw, and then this is equal to, and once again over here you'll have cos square, sin square, and minus kv square as a common factor, so this will just be minus kv square in total, and then you'll have g sin theta. Okay, so this is our first equation, and the second equation we can do a similar thing. Now this time we'll multiply this by sin theta, this by cos theta, and we'll subtract them. So we'll do 1 into sin theta plus minus 2 into cos theta, and now these two terms will cancel out. So these two will cancel out, and then you will have these. So for this you will have minus sin square theta d theta, and you will have minus cos square theta d theta because you are subtracting it. So you can take minus d theta by dt common, and then you will have sin square plus cos square, which is 1. So this will be minus d theta by dt, and over here you will have minus kv square sin theta, and you'll have plus kv square, minus kv square sin theta cos theta, and plus kv square sin theta cos theta, and they will cancel out, and we can just look at this part, which will be g cos theta. Oh, and by the way, I messed up. There should be a v over here. So I just realized that because the dimensions weren't matching in this equation, and then I realized that we had used the product rule. So you will have dv by dt over here, d theta by dt over here, theta part stays as it is over here, and v part stays as it is over here, but I forgot about the v part. So I've multiplied it back in, and now our equations are all set, and it's dimensionally consistent. So now we can use these equations, and we can take this minus sign to the other side because it looks ugly that way, and we can also take the v over here, so we have just an equation for d theta by dt. And now we have finally found the ultimate equation for both of them, but once again this is a problem because we have two unknown functions and two equations, two differential equations, and as it is, one of them is not easy to solve. Now we have two. So you may think that this is a really big problem and we can't proceed any further, but in fact we can, because if you realize, if we divide, so let me name these equations 3 and 4. So if you do equation 3 by equation 4, then you will have dv by dt divided by d theta by dt, and the dt's will cancel out. You will just have dv by d theta. And I said that the math plays out in our favor because on the RHS, both of the RHSs are just dependent on v and theta, but not directly on t. So on the RHS, we'll just have a function in v and theta. So that means that we can just forget about t and we can solve for v in terms of theta. So if you divide these two, you will get kv square. So I don't have space here, so maybe I'll get rid of this and then I'll write it. Okay, so finally we have an equation with one function and one variable. So now we are looking at v as a function of theta instead of t, and we've just forgotten about the variable t. So theta is a variable and v is a function of that variable, and now we have an equation, a differential equation for v in terms of theta. So dv by d theta, if I just simplify this a bit, is equal to kv square plus g sine theta, the entire thing into v over g cos theta. And you can also write this in one other form, which is kv cube over g cos theta plus v tan theta. And that's the differential equation. So the plan is that you solve this differential equation, which is now pretty easy to solve, and you will get v as a function of theta. So let's say that v as a function of theta is, let's say, some f of thetas. So once you get that, you can go back to your original equations, which gave you dv by dt equal to something and d theta by dt is equal to something. And now you can replace v with f of theta, because if you remember, this was, I think, minus g cos theta over v or something like that. If I'm wrong, then please excuse me, just I'm giving an example. So since we know that v is equal to f of theta, you can put f of theta over here, and then this becomes a proper differential equation with a function which is theta of t and a variable which is t, and you can solve for theta of t using this differential equation. And then since we know that v is f of theta, once you find that theta is equal to, let's say, some function of t, g of t for example, then v will be f of g of t. And this is how you can solve for the speed and the angle completely. But that doesn't work out because the solution for this differential equation is really complicated, and if you plug that in over here, then this differential equation becomes unimaginably hard. So like I put this differential equation in a differential equation calculator or solver, whatever, and I got a solution, and just to write that solution I required the entire length of my board, and it had fractions, so it was also long in this dimension. So you can imagine how complicated this will become, and differential equations are anyway hard to solve, so who's going to sit and solve this? Anyway, I hope you enjoyed, and you can solve this thing if you want, and you will get v, the speed, as a function of the angle, and maybe you can run some simulations on that. So I guess I'm done over here. This is what I wanted to show you guys, the differential equations of projectile motion in 2D with air resistance. I hope you enjoyed. I hope you try out making a simulation on maybe Mathematica. I tried it out, but it crashes all the time. So anyway, thanks for watching.